Is this better? No? Can you hear me now? Oh, good. Okay. So last time we talked a lot about graph coloring. We showed it's NP-complete, even for the special case when you have three colors, three colorability, even for the special case when the graphs are planar, even for the special case when the graphs have low max degree of 4, it's still NP-complete, or all combinations, all restrictions simultaneously, planar, three colorability, and max degree 4 graphs, NP-complete still. So there's something that's very difficult about graph colorability, assigning graphs, graph nodes colors in an optimal way. And there's lots of applications of this problem. It's very ubiquitous. So for example, in scheduling, when you need to schedule a bunch of jobs, there can be processes on a microprocessors, there can be actual jobs in the real world, construction or whatever, and certain jobs depend on other jobs. Like for example, you cannot build a building before the foundation is laid out, and you cannot build a foundation before the basement is dug in, below the foundation and so on. So you can model jobs as nodes and conflicts or precedence constraints as edges, and then whether a job can in total be accomplished in some minimum number of steps or phases is equivalent to graph coloring, actually, because you can color nodes that don't have any conflicts between them using the same color, because they're not neighbors in the colorability graph, and so on. So the time to finish a job, the minimum number of steps or time phases needed to finish some job is equivalent to the number of colors, the minimum number of colors necessary to paint the job constraint graph. So that's one ubiquitous examples. There's many examples. Compilers, when they compile code and assign registers to variables, registers in the CPU, which variables can be stored in what CPU variable registers, use graph coloring to determine the minimum number of registers needed for a particular job that runs on a CPU. So here you assign registers to nodes, and register conflicts, you model them as edges, because some registers model quantities that are related to one another, or one needs to be computed first before the other can be computed as dependencies. So you model the dependencies between variables as edges, and so the minimum number of colors necessary to color this graph constraint, register constraint graph is exactly the number of colors, the minimum number of colors necessary to paint, to colorize this constraint modeling graph. And compilers do this all the time. So compilers internally use graph coloring heuristics to come up with minimum register allocations for various compiled codes and so on. Now, obviously, compilers are not going to compute this problem precisely, exactly, to the highest degree of optimality because it's NP-complete, but they'll use heuristics, fast heuristics to do that. Okay, so there's a lot of applications of these graph colorability problems and satisfiability and so on. So again, reminding ourselves where we are in this map, P and NP, we explored in greater depth. We took a deeper dive into this vicinity of the complexity hierarchy, the Chomsky hierarchy, polynomial time deterministic and non-deterministic polynomial time, and of course both are contained in polynomial space. They're all decidable. Now we started to analyze how fast can you decide things once we know they're decidable. Any questions about any of it so far? And not all NP-complete problems come in the same kind of level of difficulty and complexity. They're all polynomially related. So if you can solve one efficiently, you can solve all of NP efficiently, deterministically. But that doesn't tell the whole story. Some NP-complete problems are more approximable than others. Some have very good approximation heuristics or approximation schemes. You can approximate some of them to within twice the optimal guaranteed. And we're about to prove that for several different problems, including traveling salesmen. Others in NP, other NP-complete problems cannot be approximated to any degree of bounded constant times optimal. And we have results to that effect. People have been proving results to that effect. So some problems are less approximable than others, even though they're all NP-complete. Some are arbitrarily well approximable. Some problems can be approximated to any 1 plus epsilon times optimal to within any epsilon that you want, however small. In other words, arbitrarily close to optimal within a multiplicative factor of optimal. And some can't. Some cannot be approximated better than any constant times optimal, unless p is equal to np, of course, in which case they can all be solved optimally, exactly optimal in polynomial time. But that's not likely to happen, and most researchers in this area believe that's not true, that p is not equal to np. Also, there's issues related to the problem size, the instance size. So some problems that are NP-complete are so difficult that even solving a problem of instance size 10 or 20 is very, very difficult, computationally intractable, even if you do it brute force for a problem of size 20 or less. For example, traveling salesmen, random cities, random weights, random graph. It's difficult to solve in general, but specific instances for geographical TSP instances where the distances represent not just Euclidean distances, which satisfies a triangle inequality, but actually correspond to cities on a map. Specifically, those tend to be easier to solve, and you can solve instances of size a few hundred cities or even a few thousand cities optimally in polynomial time, even if you use brute force. Even though the problem is NP-complete, you can solve it, medium-sized instances of a few thousand cities reasonably quickly in a brute force manner. Branch and bound, typically, approaches, where you try to prune large portions of the search space if it's not going to yield better solutions that you've seen so far. Other NP-complete problems like satisfiability can be solved brute force still in a practical way for instances of size millions. So in fact, there's NP-complete kind of forums every year in terms of conferences where they have contests who can solve the largest classes of SAT instances, satisfiability. And people have SAT solvers that can handle millions and millions of variables and probably hundreds of millions of clauses in a practical but brute force way using branch and bound. You're not exponentially looking at all possibilities, but you can still solve it exactly if you're clever and tricky and use branch and bound techniques to avoid re-exploring solution space regions that aren't likely to yield optimal solutions. Any questions about any of that? So it's not all bad news in terms of NP-completeness. And back to the first bit of good news, some NP-complete problems have approximation heuristics that are very good, and we're about to talk about that. So when it comes to algorithms, you can have speeds that are fast or slow, and you can have solutions that are exact or approximate. Ideally, you want an exact solution fast, right? You want a solution that's short and sweet, gets the exact solution, ends quickly, and that's the best of all possible worlds. Now in practice, often if you insist on being fast, best you can do is approximate a solution, right? If you want the exact answer, you'll get it slowly but surely because you'll be doing brute force exploration of the space. But in reality, we opt for fast and approximate solutions. That's what, you need it fast. You can't afford to wait days or weeks or months of CPU time for an exact answer. So you get some quick and dirty solution, not going to be optimal unless you can stumble on the optimal by luck, but that's rare. But you will get an answer and it will be happening fast. Some problems are so difficult, even approximation schemes take forever to run, very, very slow. So you get your answers too little, too late. So in reality, we rather be in this quadrant of the solution space. You want approximate answers that are pretty good, close to optimal ideally, but you want them fast, within seconds or minutes or even fractions of seconds if you're FedEx or anybody that needs to solve NP-complete problems on a daily basis to conduct their business. So the idea is that you want to avoid getting trapped in local minima and instead try to find global minima, but the solution space is convoluted and complex, and so diagrammatically, here's a local, here are all minima in the solution space. These are local minima here, that's a global minima. So if you use greedy approaches, like greedy descent kind of approaches, starting from random places, you get trapped in local minima if you keep improving your solution kind of blindly in a greedy way. But you're not likely to find the global optima, and because those could be deep in narrow, very narrow, deep crevasses here in the landscape. So the global optima might be here, but you'll never find it because you'll get trapped in a multitude of local optima because you use greed or some other approach that's not guaranteed to find the optimal. Now, this diagram is very simplistic. It just shows kind of diagrammatically, notionally, this issue in 2 dimensions, but usually the solution space is many dimensional. It could be millions of dimensions, 1 per variable, and it's a very complicated landscape. So when you use heuristics, you try to avoid getting trapped in local minima and instead try to maximize your chance of finding better minima and ideally, some global optima if possible. So some intractable problems cannot be efficiently approximated, even close to optimal. And so we use heuristics that are relatively simple to try to find these global optima if possible. Ideally, you want your heuristic to be provably good. In other words, you want some theorem that guarantees that the solution will never be worse than twice optimal, say. And that's hard to come by such proofs, but whenever you can prove them, you're good, because that's almost an insurance policy kind of guarantee that you'll never be more than, say, a certain amount more than the optimal, which, for example, if you're FedEx or AT&T, you're trying to create a fiber optic network or deliver packages and goods, if you use a provably good heuristic, you guarantee that you'll never spend more than twice what you had to spend if you knew the optimal solution, but you don't because it's an NP-complete problem. But that's a nice, warm, fuzzy feeling that you get when you have such a guarantee. Because you may be 10 times off the optimal or 100 times. It could be astronomically far away from the optimal, and that's not great for business because you're wasting a lot of resources. So slower heuristics are kind of branch and bound type approaches. You try to prune the solution space as best you can. Those take longer, integer linear programming. In fact, for a lot of these, we don't know how to do them optimally, but you can approximate solutions. And then there's kind of wishful thinking type of approaches, which if you're not sure what else to do, you throw these type of approaches at the problem, like simulated annealing, which mimics kind of a physics temperature-based kind of annealing process, where if the temperature is high, you kind of jump around the solution space looking for different regions and then descend greedily. As the temperature decreases and quenches, you take smaller steps and it reverts back to greedy descent and local search. And genetic algorithms is another kind of wishful thinking approach where you try to mimic kind of natural evolution and hybridize reasonable solutions together in the hope that they'll yield better solutions, when combined together. But it's hard to predict what kind of solutions these will spit out. They take a long time to run. These are kind of last resort type of algorithms if you have no other thing that works. So I would discourage you from throwing kind of generic solutions at problems without thinking about the problem, the structure of the problem, trying to analyze instances and solution types, and maybe you have special cases that can enable you to take shortcuts and find better optima rather than get trapped so much in local minima. But don't try kind of last resort approaches unless all else fails, right? You don't pull out heavy artillery to solve a tiny, nuisance of a problem. So let's look at specific examples. We're about to show that vertex cover can be approximated no worse than twice optimal. And we'll see a very simple heuristic that achieves that, and we'll prove that it's no worse than twice optimal. So what's minimum vertex cover? Given a graph, find the minimum set of vertices that touch all the edges. So for example, here's an input graph, a simple one with 5 nodes. And if you pick this set of 3 red vertices together, they touch every single edge in the graph. The question is that the best vertex cover that you can muster? You want smaller covers, those are better, right? Use fewer vertices to cover all the edges. So here's a better solution. This one only uses 2 vertices, not 3, and between these 2 vertices in red, they still touch every edge in the graph. So that solution is better. It turns out for this particular instance, 2 is the best. You can't have a solution of size 1 for that particular example. Lots of applications of this in communication network design and EE and civil engineering and bioinformatics and genomics and so on. And this is also one of Karp's original 21 problems that he showed at NP-Complete in that paper that we talked about a couple of lectures ago. Okay, so you might ask, why is this so hard intuitively? Well, if the graphs get complicated, it's hard to see which nodes you should select in order to touch all the edges and whether there's a better solution than what you have in your hands right now. And here are some solutions for more complicated graphs. The green nodes are the proposed vertex covers. And it's not clear for any one of these if there's a better solution than the one highlighted in green. Okay. So a few facts about this particular problem. It's been around for decades, Karp, 1970. But even before that, people have been trying to solve it because it's ubiquitous and it solves a lot of other real-life problems if you can get a handle on how to solve this problem. So we know it's NP-complete, even for planar graphs of max degree 3. That's a theorem. Another theorem is that the minimum vertex cover can be solved exactly if you want to expend exponential time. That's not hard to see, right? Look at all possible ways of choosing vertices as subsets out of the original set of vertices and check each one to see if it's a cover. And before you exhaust everything, once you exhaust everything, you'll know what the best cover is. But that's exponential time. Now, we know that it can't be approximated better than 1.36 times optimal. That's a non-approximability result. That's a lower bound on any approximation whatsoever. That result is hard to prove because I'm not a millionaire kind of a proof. This basically says that no possible heuristic or approximation scheme for the vertex cover problem will give you solutions that are guaranteed to be at least no worse than 1.36 times optimal. Now that's not to say that one day we could prove better results than this. In other words, smaller upper bounds on the approximability, the non-approximability of vertex cover. Maybe, or maybe, excuse me, I said it reverse. Higher lower bounds on the non-approximability with respect to constant times optimal. So maybe one day somebody will show you can't do it better than 1.4 times optimal, unless p is equal to np, of course. If p is equal to np, all bets are off. We can solve this exactly in polynomial time, as we would be able to solve exactly every problem in NP, including NP-complete problems, in polynomial time as well. And the good news is we can solve this within no worse than twice optimal very quickly. In fact, within linear time. And we're about to show that heuristic and prove this theorem. So this theorem will prove. The other ones we won't. Well, this is easy to see. Exponential time suffices. This is a hard theorem to prove. We won't do it here. So the idea is very simple. Pick an edge, add its edge points, endpoints of this edge, the 2 vertices incident to this edge, and then just repeat, and at the end you'll get a vertex cover. It's no worse than twice optimal. So here's the algorithm in more detail. It'll run in linear time. It'll produce vertex covers no worse than twice optimal. Okay, so here we'll have a running example. So again, you pick a random edge. Which edge? We don't care. Just pick one. Like pick this edge here. And then add both of these vertices that this edge touches into this growing vertex cover solution. Okay. So add x and y to the solution, and then eliminate this vertex x and vertex y and the edge between them, like that. And then throw those edges and vertices away from the graph. And then for the remaining graph, repeat this process. Right? So do it repeatedly. Pick an edge, throw both of its endpoints, vertices, into the growing solution, eliminate that edge and its 2 vertices, repeat. Okay. And at the end, output that growing set of vertices that you accumulated throughout this process. That's it. That's the entire heuristic. So it's very simple. It runs in linear time. And the analysis of this, why it's twice optimal, is also relatively straightforward. And the reason is, you look at this edge in red, connecting the x and the y, and in any vertex cover that must touch every single edge, at least the x must be in that cover, or the y must be in that cover. Otherwise, the red edge won't be covered if both x and y vertices are absent from your solution proposed vertex cover. How many can see that? At least one of the two must be there. One of the two vertices must be in any solution, right? Never mind the optimal solution. Any vertex cover that touches all edges. So at least the x must be there, and at least the y must be there. Otherwise, the red edge will not be touched by the solution, and so it won't be a vertex cover. And you threw both x and y into the heuristic solution that you spat out by this heuristic, this algorithm. So one of them had to be there, but you threw in both. So you keep doing this. For every edge that you pick and throw both vertices into the solution, at least one of the vertices must have been in the optimal solution. So once you keep doing this, whatever solution you spit out, these accumulated vertices, these red vertices that you accumulate throughout this process, will not be more than twice the absolute minimum that the optimal solution must contain no matter what. How many get this? Because you keep throwing 2 every time you need 1. Not 3, not 5, but 2. And one of them better be there in the optimal solution. And you keep doing this. So the amount of vertices you'll end up with is no worse than twice what the absolute minimum has to be. Okay, any questions so far? So this will give you no worse than twice optimal, guaranteed, for an NP-complete problem. And not just for an NP-complete problem, but an NP-complete problem that cannot be approximated better than 1.36. And here we have a solution that's no worse than twice. So we're pretty close to the best possible in polynomial time, but the best possible bound of approximation for an NP-complete problem. So this is an approximate heuristic for an NP-complete problem, and that's the best known to date, even though this was proposed in 1974. So this was proposed, some 40 plus years ago, and to this day, it's the best we got in terms of approximation to the vertex cover problem that runs in polynomial time. And this doesn't just run in any polynomial time, it runs in linear time. Right? So it runs very, very fast. So this is an example of how to approach approximations to NP-complete problems and prove that the approximation is pretty darn good. It's not just some hand-wavy, okay approximation. It's guaranteed, mathematically, to be no worse than, say, twice the optimal. And in practice, if you run this, of course, will it be twice the optimal if you run it on random graphs with random edges? You think a lot of the time it will be 2 times optimal or close to 2 times optimal? How many say yeah? How many say, no, it'll be a lot closer to optimal than to 2 times optimal? Yeah. Why? This theorem says 2 times optimal. So why won't solutions come out to 2 times optimal?
Because it's unlikely you'll get exactly 2 times optimal, so it's probably less.
Yeah, this is no worse than 2 times optimal. Doesn't mean it's equal to 2 times optimal. Often you will luck out and the answer will be optimal. How many see that? The answer of this heuristic can be optimal if you're lucky. Of course, luck is not a very good algorithm or life strategy for that matter. But it could happen. So when I say 2 times optimal here in this theorem, it doesn't mean that it'll be anywhere near it. This is an upper bound. It's guaranteed never to be worse than 2 times optimal, bigger than 2 times optimal. But in practice, it'll often be less. And that's typical of NP-complete heuristics, NP-complete problems. When you solve them with approximation heuristics that run in polynomial time, often they'll be pretty close to optimal. So if you run this heuristic on random graphs, compute the optimal, compute this heuristic, compare the two, keep running this millions of times, and take the average performance of this heuristic compared to optimal, it'll probably be no worse than 10% more than optimal or 5% more than optimal, something like that. That's typical. It won't be 1.8 to 1.9 times optimal. Because for that to happen, you'd have to be very unlucky all the time. And that's not very probable. Right? I mean, another way to think about it, if If you go to Vegas and keep gambling and gambling and gambling, the chances are very small that you'll win all the time. In fact, if you did, Vegas would be very boring and people wouldn't gamble if they won all the time. There's interesting kind of psychology behind that. On the other hand, it's not very likely that you'll always lose every single time from thousands and thousands of plays, whether it's blackjack or roulette or whatever. That's not likely either. Okay? It's the same thing here. You're not likely to get the optimal every single time. In fact, if you got the optimal every single time, you'd be solving NP-complete problem in a linear time here. But you're not going to be terribly off base all the time. And if you are, no worse than 2. And that'll be a rare occasion. So the average will be a lot closer to optimal than to the bound that you're proving. That's a general trend in heuristics. Okay, any questions about that? Now in practice, you can still do better than this heuristic on average. How will you improve the average performance of this heuristic and still retain the 2 times optimal bound? In other words, modify this heuristic for me to likely do better in practice.
Really go through your set and try to remove each one, and then go through it again and try to remove one.
Yeah, so you can try to remove. So let me turn the question more specifically to this. Here we picked a random edge xy. You picked it randomly. What edge do you think you should pick instead of a random edge if you thought about it a little better? And remember what you're trying to do. You're trying to find the minimum number of nodes that between them touch all the edges. So which edge should you pick if you have a choice? Because random is whatever edge you like, which means you have a lot of choice. You have a lot of leeway. So what would you like to do? Yeah, so you pick an edge whose endpoints have the highest degree between them. How many get that? That's a good thing to do because that's exactly what you're trying to accomplish. The minimum number of nodes that touch the greatest number of edges. So pick nodes with highest degree. And if you do that, will you still have the 2 times optimal bound if that's your criteria for selecting? How many say, yeah, you'll inherit that bound? How many say, no, the bound will no longer hold because you were supposed to pick a random edge? How many say the bound will still hold? Okay, that's better. Why will it still hold? Why won't you lose that bound all of a sudden? Straightforward. Yeah, so this bound holds for any selection of any edge, including random edges, or randomness can come in many flavors. And so if it works for any edge, it'll work for a particular edge that has highest degree of these two adjoining nodes. The sum of, say, the sum of degrees is the highest. That's easy to find out and do still in linear time. And now it'll terminate sooner, potentially. And if it does, it'll terminate with fewer nodes and a better cover, better vertex cover. That's a quick example of how to modify heuristic in a way that'll not just have it terminate sooner, but give you a better solution and still inherit this best bound. Because you don't want to lose that bound by modifying the solutions. All right. Any questions about that? Just for giggles, let's modify it some more. You know, how else could you modify it to potentially get better solutions? A node edge that what?
Don't choose an edge that is connecting a node that's already been selected.
Okay. Choose an edge connecting a node that's already been selected to another node that hasn't been selected, but maybe with high degree. Yeah, you can do that. Let me ask you the following heuristic. Instead of picking an edge and throwing into the answer both its endpoints, why not just pick a node with the highest degree, eliminate that from the graph, and repeat that? Pick the node of highest degree, remove it, and all of its edges, of course. For the remaining graph, repeat that. Find the node of highest degree in the remaining graph, throw that into the solution, repeat until no edges are left. And then you got a node cover. How many say this will work? Okay, what's the problem with that in this context?
Would updating the graph cost more help?
What's that?
Would updating the graph take a cost more?
Updating the graph will cost more time? Maybe, maybe not. But even if it costs more time, won't it be polynomial time? So we're still okay. That's a polynomial time heuristic, right? And if you're careful, you won't take longer than linear time. But even if you took longer than linear time, that'd still be okay as long as it's polynomial, and that's certainly polynomial. It doesn't blow up the time to exponential, but you know, it's an interesting observation. You certainly don't want to expend more time than you have to. What else? Any other issues? If we pick an arbitrary node with highest degree, remove that. You will lose your 2 times optimal bound. How many see that? Because that node that you pick may not be in the optimal. So by throwing it into the solution, you're increasing your solution size, and you could do that unboundedly. How many see that can happen? How many see an example where this can happen? This can happen. I'll leave it up to you to come up with a counterexample that actually shows this could yield arbitrarily far away from optimal. Because certainly if you pick a random node, let's say you pick a random node as opposed to a random edge, and throw that into a solution, eliminate its edges, repeat, that could be arbitrarily far away from optimal. Let me give you an example, just so you see how these counterexamples work. So take the graph that looks like a bicycle wheel. You know, so you have n nodes around that. If you pick an arbitrary node, not edge, but node, single node, throw that into the solution, eliminate its neighboring edges, and repeat, you could pick this node, eliminate that edge, and pick this node, and you can pick that node, you can pick that node. Arbitrary nodes, but really the node that you should have picked at the beginning is this one. But if you pick an arbitrary node and throw it in and do this algorithm, but picking nodes, not edges, you lose your bound because you'll get a huge vertex cover here involving all the nodes except one, where the best solution is just a node cover involving this node and nothing else. So by picking n nodes, you're n times away from the optimal, not even twice optimal, not even 15 times optimal, not even 1 billion times optimal. You're n times optimal for arbitrary n as n grows. So that's a terrible heuristic, picking an arbitrary node. Now, before we talked about picking the highest degree node, and in this example, if you pick the highest degree node, that will work okay for this example. But there's other examples where picking the highest degree node will fail miserably also. Okay. So it's important here to pick the highest, or to pick an edge, not a node. Okay. Now, so if you pick a highest degree node, that's pretty good, but it won't have the 2 times optimal bound. But if you pick the highest degree node, you may get a better solution when you actually run this than with this picking some random edge, or even the highest degree edge, highest degree pair of nodes edge. So how would you use this heuristic here that I drew on the board, highest degree node, repeat, and still retain the 2 times optimal bound at the same time, and still be within polynomial time, of course, because we're talking about heuristics, so exponential time is off limits. If we could use exponential time, we'd be solving it exactly, dispense with all these heuristic stuff, brute force search. Right? So how do you implement in practice a best highest degree node repeating solution that potentially could be better than this, but the downside of this solution is that it loses the 2 times optimal guarantee. So my question to you is, how do you get the best of both worlds? How do you run this solution and still have it inherit the 2 times optimal bound that is very dear and near to our hearts, that we want to keep and maintain and preserve and not lose? You can do this, and it's not that hard to do. How would you do it? This is testing your MacGyverness after a whole semester of clever algorithmic approaches to interesting problems. How would you do that? Yeah.
Okay, so take the highest degree node, remove that, but also pick one of the nodes that's connected to it without two.
Okay, so pick the highest degree node, remove that, and also pick one of its neighbors and remove that too, or add that to the solution too. And presumably, that neighbor should have highest degree also among the remaining neighbors. Okay, that's similar to what we said earlier about picking the highest degree edge. In other words, edge with the highest sum of degrees of its two nodes. Okay, that would work. That would work, but that's kind of similar to what we did. What if we ran this to completion and got some solution? That solution would be arbitrarily far away from optimal because there's no bound.
Oh, then repeat with a solution that we know has the bound.
Yeah. Repeat with a solution that we know has the bound, i.e. the one on the slide, and then what? So now I have two solutions.
Hold up the new solution as your final solution.
What's the new solution?
The solution that you got your first solution, and then you take that as the input to using the method that we described previously, and then the output of that
Well,
is your final.
yeah, so you can't take the solution and use it as an input to it, because the solution is just a vertex cover. It doesn't have any edges at all, right? It's just a subset of the vertices, but you're on the right track. So his suggestion was to do both, but we're still not closed the loop here on what to do with these two solutions.
But if we just invert all the points.
Invert all the points?
Right.
Okay. That has potential, but let's chase this down. So we have two solutions. We have this solution here that doesn't have the bound, and we have this solution here that has the bound, but could be worse than this solution. Bigger, more nodes here than this. How many see that could happen? Okay, what do you do with these two solutions? It's not a trick question. Take the better of the two. If you take the better of the two, what do you have? What kind of a solution do you have? You're certainly not worse than either one because you take the better of the two. But what about the bound for the better of the two? It's still in effect. How many see that? Because one of them had the good bound, and one of them was potentially better without the bound, just better, just smaller, less nodes. So if the larger one had the bound, and you got something better than that, that must have the bound too, because you're smaller than something that had the bound, even though in general this algorithm doesn't have a bound. But in practice, on a single instance, if it's better than another instance that you computed that has the bound guaranteed, this better one inherits that bound because it's smaller. How many see that? How hard is it to run this one and that one? What's the time complexity of running both as function of the size of the graph? Still linear. This is linear, this is linear, so twice the time you'll get a solution that's potentially better and still has the bound. This is a meta-heuristic. Right? We talked about meta-heuristics before. You run two heuristics, take the best of the two solutions, and you inherit the properties of both. Ideally, it's the best of both worlds. It'll be smaller in practice and better in theory than the one that doesn't have the bound. Could you do this with 3 different algorithms, 4 different, 5 different algorithms? How many say, yeah, you can pull this trick? Yeah, this is a general Jedi trick. You can do this with any number of algorithms, right? It's beautiful. It's a general meta-algorithmic approach. Compute several solutions. Take the best of them. If one has a guarantee, you inherit that guarantee. If another one has a better solution for that instance at hand, you're better off too, and you still have the guarantee, the mathematical upper bound insurance policy. Beautiful. It's rare when you can do that, bash together a bunch of solutions and get the best of both worlds, as opposed to you got to pay the piper somehow, and there's some drawbacks and there's trade-offs. Of course, you do pay the piper something here. What do you pay?
You're still running it in practice twice.
Yeah, you're still running it twice. You're running this one and you're running that one. That's 2 runs instead of 1. But if you have two cores, it's not even twice real clock time. It's just twice the CPU cycles, but running in parallel. Or you can write it serially, it doesn't matter. But paying twice for something that's a lot better, that can save you money when you're designing, networks and schedules and, delivery times for traveling salesman tours and fiber optic networks using Steiner to you. Paying twice in CPU time is a small price to pay for getting a better solution to an NP-complete problem that we have no idea how to solve exactly in polynomial time. That's a good deal, algorithmically, in case you're not sure. Okay? It's a bargain, actually. You should take it and run if you can. That's kind of a deal. Okay, any questions about that? And that's a general technique. You can do this with any kind of algorithm, heuristic, or problem. You can even do that with sorting. Give you an example how powerful this technique is. How fast does merge sort work? Worst case. And log n time. How many know that or heard about? Good. Quick sort. Worst case behavior of quick sort. How fast or how slow is that? N squared. It's quadratic. How many knew that? Know that. Okay. How do you modify quick sort? But quick sort runs much faster than the other algorithms on average. Even though it has a bad worst case of quadratic, on average it's n log n, and on average it's low constant n log n. That's why we call it quick sort, because it is fast. How would you modify quick sort to run in worst case n log n guaranteed and still enjoy the quick behavior of quick sort? Hint, use the Jedi trick we just mentioned.
Run quick sort and merge sort.
Yeah, run quick sort and merge sort in parallel on the same input. One of them will finish first. Whichever finishes first, present its output as your own. Right? So this will run in time very similar to quick sort. In fact, how much slower it is than quick sort doing both of these together. Half speed. Why? Because if one tries to run much longer, the minute you get the other solution, abort the other one. So you never will be worse than twice the speed, or half speed, I should say, twice the time to completion. But now you have the guaranteed n log n upper bound insurance policy on the runtime. Never worse than n log n, and on average it'll be very, very quick, because it's quick sort. You're running in parallel. How many get this? And that's a modification to quick sort in an abstract level. You didn't go into the internals of quick sort and futz around with it, even though you could do that too, make quick sort run in n log n time guaranteed also. There's techniques to do that, but they're much more complicated, harder to explain, or harder to analyze. Here we use quick sort as a black box and modify it by wrapping code around it that aborts it after n log n time if it doesn't finish on time, if it's too slow. And guess what? If you do this, you don't have to worry about the input distribution. You don't have to worry about which inputs to quick sort will make it be sluggish and run in quadratic time. You don't care. It'll always finish in n log n time one way or another, either on its own, or you'll abort it because something else was faster than it. So you see how powerful this technique is. You can apply it to almost anything. You can apply it in real life. Give me an example from real life where you can do this. This will work beautifully. No, let's say there's some ceremony. You need a cake. You need a wedding cake or bar mitzvah cake or cake, and the cake better be there because there's 100 people waiting, and but you're not sure if the baker you hired is up to snuff. That'll meet the deadline. Maybe they don't know what they're doing. You don't know them very well. And if the cake doesn't arrive, it'll be a disaster of large proportions. Okay, what do you do? Algorithmically, what would you do in real life?
You go buy a worst cake and store it just in case you have it.
Yeah, how would you say it perhaps differently in this context? Yeah, order 2 cakes from 2 different bakeries.
Yeah, but neither of the bakeries have it down.
Sure, but I see what you're saying. So you want to order it ahead of time and store it, maybe freeze it or something, and then there'll be your backup cake, right? And if the real cake doesn't arrive, at least you'll have a cake, and you'll thaw it out or whatever. Or you can order 2 cakes from two bakeries, and the chances now that both of them flake out on you will be much smaller than before. Of course, the price you pay is what? This costs you twice the cake budget that you had before, but you don't have to worry about not having a cake altogether. So in real life, you can do this too. It's called hedging your bet. How many heard that phrase? That's exactly what it is. Venture capitalists do this all the time in Silicon Valley. They don't fund one startup. They found 20 startups. They're hedging their bet. They don't care which 19 fail, as long as one succeeds, they'll be good. So that kind of strategy, hedging strategy, goes a long way, gets a lot of dividends, literally, monetarily or otherwise, or complexity-wise. Okay, so let's do this for another problem. You see how it goes. Any questions, by the way? Maximum cut. You have a graph, and what you want to do is find a partition of this graph into two subsets of nodes, and the cut size is the number of edges crossing the cut. So you want to maximize the cut size. You want to partition the graph into two sets of nodes, two subsets of nodes, such that the greatest number of edges cross the cut. Okay. So here the cut size is 2, but if we flip a couple of nodes around, the cut size becomes 4 now. I put the A on the same side, but put the D on this side, the C goes over there, and now the cut size becomes 4. Is there a better solution than this for this example? Increasing the cut size even more? Yeah, move the E across as well, and now you have a cut size of size 5, and that's a better solution. Can you do better than this for this example? No. Why? There ain't no more edges, right? So all the edges cut, go across the cut, so it ain't going to do better than that, right? There's no more edges to go anywhere, never mind go across the cut. So lots of applications of this problem in VLSI design and communication networks and physics. And again, this was one of Karp's original 21 problems. So let's come up with a heuristic for this NP-complete problem, for which we have no idea what the best kind of polynomial time solution is, or whether there's a polynomial time solution. Otherwise, P will be equal to NP if there was. But very fast, you can come up with a cut size that's no worse than twice the optimal. Or put another way, it's at least half the best possible. Okay. Now, a few issues about this before we even show the heuristic. The maximum cut problem can be solved in polynomial time for planar graphs. So if a graph is planar, we know how to do this exactly in polynomial time. But planar graphs is a very, very special kind of graph. In fact, there's another theorem that says, anyway, let's just say that. Now, that's not a trivial statement, because for planar graphs, other NP-complete problems were still NP-complete, even if you restricted them for planar graphs. Remember three-colorability for planar graphs? That was still NP-complete. But maximum cut for planar graphs is polynomial time solvable, and we know how to do that in polynomial time. All right, a lower bound on the approximability. This problem cannot be approximated better than 17 over 16 times optimal. Somebody proved that theorem. That's hard to prove, because you have to show that no heuristic in the universe can possibly solve this better than 17 over 16 times optimal, unless P is equal to NP. But we know how to solve it no worse than twice optimal. We're about to prove that. Right? So how do you solve it no worse than twice optimal? And by the way, twice optimal for this one is not the best known. The best known right now is 1.14 times optimal, like maybe 1/7 or whatever. And notice that 17 over 16 is 1.06. So we know how to solve it within 1.14 times optimal, but we know we can solve it better than 1.06. But we're not going to show that good of a result. That's actually a very complicated heuristic, even though it's polynomial time. We'll show something a little more lax, twice optimal. And that we can show quickly because it's pretty simple. All right. So how do you do it no worse than twice optimal? Ask yourself if, first of all, start with a random partition, randomly distributed, Ask yourself then if moving an arbitrary node across the partition will improve the cut size, i.e. increase the cut size. And then repeat until no further improvements can happen. So it's very simple. Find a node to flip across the cut that increases the solution quality, and keep doing that back and forth, flip nodes across the cut, as long as each flip increases the solution quality, increases the cut size. And when you peters out, when you can't do it anymore, stop, and that's your heuristic answer, your approximation. That's no worse than twice optimal. We're about to prove that. So for example, here, start with a random partition, right? I don't care which. Cut size is 2. And then find a node to flip. So for example, we flip the E across, and that increases the cut size from 2 to 3, because now 3 edges cross the red cut. And that's it. We output that because no more nodes can be flipped in order to improve the solution. Now, of course, the optimal solution, we already see that on a couple of slides ago, is size 5. But the 3 is at least half of the 5. Because half of the 5 is 2.5, and 3 is better than that. And this is guaranteed in general to be at least as good as half the optimal or better. In other words, the ratio to optimality is no bigger than 2. So how would you prove that? Well, how would you characterize a node so that when you flip it to the other side, it'll increase the cut size and improve your solution? What about that node must be true for this to be the case? It has to have edges that aren't in the cut, but what if some edges are in the cut and some edges are not in the cut for that node?
It has to have at least one that wasn't in the cut.
Okay, so it has to have at least one edge not in the, so the B has, let's see, so here the B has one edge that's not in the cut, it's this one. So flipping it across will improve or disimprove the cut if you flip this B across here. It'll disimprove. So you're on the right track, but let's refine the condition. What about the B makes it not good to flip it across?
All nodes that you want to flip across have fewer edges currently being cut.
Yeah. Of all of B's neighbors, more of its neighbors better be on the same side as B than on the other side. And if that's the case, it has more neighbors on its own side than on the other side. Flipping it across will lose all of its current cut edges, but gain all of its neighboring cut edges on its own side, which now are bigger, and so there's a net gain, and that'll be an improvement. So it's very easy to test this condition to see how many nodes are on your side versus on the other side. Right? And you can keep flipping it. Now, as long as there is a node that has more neighbors across the cut, more neighbors on the same side of the cut as itself than across the cut, you can flip it and improve the solution. But on the optimal solution, there is no such nodes. In the optimal solution, every node has more neighbors across the cut than neighbors in its own side of the cut. How many see that? Otherwise, it wouldn't be optimal, because otherwise you can flip that node and you get something better, so the original wasn't optimal. Right? So if every node, after this algorithm is finished, has more neighbors across the cut than its own side of the cut, which will be true when the algorithm finishes, otherwise you can flip it and the algorithm can continue improving the solution, at least half of its neighbors cross the cut for every node that's output by this heuristic. How many see that? Because if there was a node for which this wasn't true, you'd flip it and get it at a better solution because this heuristic will keep going. So when this heuristic finishes, there's no node, or let me put it in a positive. When this heuristic finishes, every node has more neighbors across the cut than in its own part of the cut. Which means half the edges of the graph cross the cut. How many see that? Good. So for every node, it has more neighbors across the cut, which means of that node's degree, there are more edges going out of that node crossing the cut than going straight to the same part of the cut, which means for every edge in the graph, that's true. For every node in the graph, that's true. And at least half the edges of the graph now are crossing the cut. And the maximum possible cut size that you can have are all the edges in the graph. I mean, see, the cut size can never exceed the number of edges in the graph. That goes without saying, right? That's the highest it can go, is if every single edge crossed the cut. But this heuristic terminates when half the edges or more of the graph cross the cut. So the solution it provides is no worse than twice the optimal. Put another way, it's at least half as good as the optimal. How many see that conclusion? Okay. I only see about 20% of you raising your hands. Any questions about that? So this is a heuristic for the maximum cut problem. It flips nodes as long as flipping nodes increases the cut size. Start with a random cut, I don't care which. When this finishes, no nodes can increase the cut size. That means the outgoing edges, half of the outgoing edges out of every single node cross the cut at that point. Otherwise, you can flip such a node and get a better solution from this heuristic, but this heuristic doesn't terminate until this is exhausted. This rule is exhausted and can't be applied anymore, which means the final solution of the output of this heuristic will be at least as good as half of the optimal, whatever that is, and often a lot better than that. How many can see that this sometimes can find you the optimal by accident, by luck, okay? And often it'll be close to the optimal, not twice as far from the optimal. So if you run this a lot of times, on the same instance, using random choices for which nodes to flip if there's ties, you'll get potentially different answers. Take the best of them, and that'll be even better on average. Right? And here we could take an arbitrary node, but we didn't have to take an arbitrary node. We could take a specific node. Which node specifically do you want to take to do a flip, ideally? That will hopefully get you a better solution to make it algorithm terminate faster or whatever. Yeah, the one with the most edges on your side compared to edges across. In other words, the difference between the two better be maximized. So the difference between neighbors on your side and neighbors across the cut should be the highest, and that's the node you flip next. How many can see that? That's a good thing to do. But that will still get you the 2 times optimal bound. Right? Okay, any questions about that? So you see, heuristics are easy to come by. You inch towards a solution. You greedily kind of make your way towards a solution following the rule that you're trying to optimize, maximum cut size or largest, smallest vertex size, or, traveling salesman heuristic, find the nearest neighbor, go there, repeat, see how that compares to optimal. Heuristics are easy to come by, and life is full of heuristics. You use heuristics all the time when, since sunrise to sunset every single day, you're alive, right? And most of them work out pretty good, and occasionally there's some big blunder, right? Now, it'd be nice to have guarantees like that in real life, but, these kind of guarantees are good to have. Doesn't mean you can't try other things and inherit the guarantee if you use meta-heuristics and use multiple strategies, combine parallel strategies and so on. Yeah?
So if you identify there's like a square-like structure, would it make the algorithm better if you kind of inverted it? Like, if you took it from
Yeah, so if you have a graph that's a square, like a 4-cycle, and the cuts 2 of them, there's no way to improve it from there. But if you took 2 nodes and flipped them simultaneously, they'll get the cut to go through all 4 edges. But this heuristic doesn't allow that. You take a single node and flip for 4-cycle, there's no improvement if you just flip 1 node. How many can see what he's talking about? Yeah. So what's a better heuristic right away?
the first time you identify a square.
Yeah. So first do this. Nail down the bound. So run this and nail down the bound. But then, why can't you get from here to here in one fell swoop? You have to flip the C and the D simultaneously. And then you'll get from 3 to 5. But this heuristic doesn't allow you to do that. It allows one flip. So flipping the C won't help. Flipping the D won't help. So it stops. So first run this and then do what? As a post-processing step. Let's be more general, rather than look for a square, because maybe you'll miss other things, like 6 cycles or 8 cycles or who knows what else. Any graph. But let's generalize. Yeah, if you look for a square and you flip, you're good. But let's make it even more powerful general than that.
Pick an edge that's being cut and try swapping the two nodes that are on the ends of it.
Yeah, pick an edge on the cut and swap the two nodes. Or even more general than that. Pick two nodes such that when you swap them both simultaneously, you win. And keep doing that. How many see that? That's powerful. Does that inherit the bound? How many say yeah? Yeah, if you do it after this is done. Yeah, so when this is done, you got your bound. And if you can keep going and win even more, the bound is still in effect, and you still get a better solution potentially that's even closer to optimal than the bound suggests. That's a good post-processing step to do. And in many heuristics, it's exactly what you do. You take your solution, then you start massaging it after the fact as a post-processing step, and you trim it a little bit and make it even better, and you get to keep your bound, and you get to win some more, potentially. Yeah?
So in this situation versus in the previous example, we actually can do post-processing because the output is something that we can continue to modify.
Yeah. Yeah. Could you do this trick here for vertex cover? Could you take the solution and then post-process it in this way to win even more? How many say you can do that? How many say you can't do that? How many say you can do it? How would you post-process a solution to get it even better?
If you have any node in your set that's connected to only nodes that are also in the set,
What do you say? Yeah, see if there's any way to swap a node in your solution with a node not in your solution in a way that will get you some better coverage. Now, if you swap a node in with a node out, the vertex cover will remain the same size. So you have to modify the swap a little bit. So what specifically could you do to reduce the cut size? I guess we're talking about the vertex cover. To increase or to decrease the vertex cover by one node. Yeah. Well, what if you remove two nodes and replace them by a single node? And look at all combinations of twos and ones. That's a lot of combinations. It's a polynomial number, though. And if you can find the triplet of nodes, 2 to remove and 1 to insert, that improve the vertex cover by 1, you're good. So that's a very simple, straightforward post-processing step, and you still get to inherit your bound, because you're not any worse off than you were before, and possibly better. So there's always post-processing that you can do, right? Traveling salesman tour. Let's say I give you a traveling salesman heuristic. He gives you a tour. How can you improve the tour once the heuristic presents you with an approximate tour? Remember, TSP is just a permutation of the cities. How many get that? It's just a permutation. That's all it is. So tweak the permutation. Take two things in the permutation and swap them. And if that improves the tour length, you win. There's only n choose 2 pairs to look at. So it's a polynomial time heuristic. And you can repeat that a bunch of times. Yeah, so there's always post-processing things that you can do. Of course, it costs you more and more time to do all that. But if you get better and better solution to an NP-complete problem that we have no idea how to solve in polynomial time exactly, that's a net win. So another meta-heuristic is how much time do you want to spend on these kind of post-processing steps? As much time as you can afford is the answer. If you have time to spare and you know the solution right now, you need it 5 minutes from now, might as well have some processor spend those 5 minutes on trying to improve the solution until you need it, and then you're worse off than before and possibly better. Right? So if you can afford to tweak it further using post-processing, go for it. If you had a lot of time, try to solve it exactly even. Run in brute force exponential time, and if you need it only a year from now, maybe it'll finish by then. And then you'll have the exact answer. You could do that too, if you'd like. Or anywhere on this trade-off curve, time versus resources. All right, well, we're on a roll, so let's talk about traveling salesmen and show how to do it no worse than twice optimal. This one is a little more involved. So you want to connect a bunch of points in the plane, you want to do a TSP tour, you want to do a good one, so we'll start with an MST, minimum spanning tree. So minimum spanning tree is shown in blue, beautiful color blue. And a tree is a good way towards a tour because it already connects the points, like a tour does, but it's a tree, not a cycle. A tour is a cycle. So we'll make a cycle. We'll traverse the minimum spanning tree in blue using the green tour. It's this depth first search of this minimum spanning tree in blue. So the green just traverses the blue depth first search. Now the green is a cycle. The order in which the green visits the nodes is a cycle. How many can see that? But it's not a TSP cycle because why? It visits the same nodes multiple times. That's no good. For TSP, you want to visit every node exactly once. So what we'll do is go through it again, follow the green tour, but whenever you're about to visit the same node a second time, like here, go to the next one that's still unvisited. So follow the green, but short circuit the green by jumping to the next unvisited node if the cycle wants to visit the same thing twice. Don't let it. Short circuit it and go to the next unvisited one. How many get that? Okay. So the red one is the short circuiting of the green's tour by not visiting the same one twice. And then when you get to the end, you go back to the beginning. So the red tour is a TSP tour. How many can see that? It visits everything once and once only. Now, the red may not be optimal, but it's pretty good, and it's no worse than twice optimal. We're about to prove that. So that's our heuristic solution, the output, the red tour. So pretty simple. Start with the MST, traverse it, depth first search, but skip everything you're about to go visit twice and don't visit it twice. Just go to the next one, and so on. Okay, why is that no worse than twice optimal? So first of all, the red tour is no bigger than the green tour, no longer in length than the green tour. How many can see that? Why? 2 words. If you stretch out the green tour with all of its edges, all its multiple repeated edges, the red is no worse than the green. Pythagorean theorem. It's close, it's on the right mindset, but where are the right triangles if you're going to apply the Pythagorean theorem? It's close. What do you say? Triangle inequality, right? How many see triangle inequality? It has to do with triangles, so you're on the right track, right? But it doesn't have to be right triangles. The point is, whenever you have a triangle, for every edge, it's smaller than the sum of the other 2 edges combined. Why? Because the shortest distance between any 2 points is a straight line. That's that edge. Right? So the red short circuits, there's all the triangles. Triangle, triangle, right? Triangle. So you're shortcutting longer green tours with shorter red tours. By the triangle inequality, you won't be any worse off. So the red color-coded red S tour that we output is no worse than the MST, which is the green total tour. Triangle inequality makes this true. Separately, the minimum spanning tree weight is less than the optimal traveling salesman tour. Even though we don't know what the optimal traveling salesman tour is, we know it's at least as costly as the minimum spanning tree. Why? Why is this true? The minimum spanning tree is always less than the optimal traveling salesman tour, salesperson, I should say, tour. Why is that true?
Because the traveling salesman has to come back and can't split.
Yeah, traveling salesman can't split and has to come back, but let's say it more incisively, more deliberately. You're right. But why is it that if it can't split, it's not going to do any better? Maybe it can do better without splitting. I give you a TSP tour. A tour is a cycle. I take one of the edges and remove it from the tour. What kind of object do I get? A cycle minus an edge is what kind of an object? Now it's a tree. It's a very pathological tree. It's a list. But a list is a tree, a long, meandering list. So a cycle minus an edge is a tree. How many see that? A traveling salesman tour is the best cycle, but it's still a cycle. And a cycle minus an edge is a tree. And the minimum spanning tree is the best tree. A cycle minus an edge is a tree, not necessarily the best tree. The minimum spanning tree is the best tree. So the minimum spanning tree is always cheaper than the optimal tour, because even if you take an edge away from the tour, making it even shorter than that, it'll still be not necessarily the best tree, just a tree. And the MST is the best tree. How many can see this inequality now? Good. So we're on a roll. So if one thing is less than another thing, right, then twice that thing is less than twice that other thing. I just multiply both sides of this inequality by 2. But the green tour is twice the blue MST, right? The green is twice the blue minimum spanning tree. How many can see that? Why? Because every edge in blue is traversed twice in green, once on the way down and once on the way up in the depth first search or traversal, right? So the red tour that we output is less than the minimum spanning tree, which is equal to twice the minimum spanning tree. Right? This traversal in green is twice the traversal of the MST, because every edge in blue is covered twice in the green tour. But we already saw that the MST is less than the optimal TSP, because you could just remove one edge from a TSP, and you won't be any better off than the minimum spanning tree, because that's the best tree, and the traveling salesman tour minus an edge is just a tree, not the best tree. So there you have everything combined, and so the tour in red is no worse than twice the optimal TSP tour. How many see the proof now? That's the end of the proof. Any questions about that? So we just proved an upper bound of twice optimal on this red heuristic tour. How fast would it be to output this red heuristic tour? What's the bottleneck subroutine, where most of the time is consumed? Yeah, it's the minimum spanning tree subroutine, which could be run in time E plus V log V or whatever. It's easy to do, or V log V, let's say, for n points in the plane, be n log n. You can do that fast in the plane. Now, this presumes that a triangle inequality holds, and in the plane, of course, it holds, and in 3 space, in 3D, it'll hold also. In Manhattan metric, in Chebyshev metric, and other metrics, it'll also hold. Or in arbitrary graph, when a triangle inequality holds, this will also hold. So this heuristic can operate in graphs. How many can see that? Not just in points in the plane. Because minimum spanning tree is defined for graphs, right? Traversals are defined for graphs, right? You can add up edge costs and come up with tour lengths and so on. But the triangle inequality must hold. Now, it turns out that TSP in general is hard. You can't approximate it in general graphs for any constant times optimal unless P is equal to NP. That's a fact. That's a theorem. For arbitrary graphs where the triangle inequality doesn't hold, you can't approximate it. We can prove that unless P is equal to NP to any factor times optimal, however large, to 1,000,000 times optimal. You can't do it. And about 20 years ago, Sanjeev Arora from Princeton showed that you can approximate it for where the triangle inequality does hold for geometric TSPs, no worse than 1 plus epsilon times optimal for any epsilon, however small. So you can choose to be arbitrarily close to optimal, not just twice optimal. There's another famous heuristic by Christophidis from 1975 that shows that you can do it 1.5 times optimal, guaranteed, in the Euclidean plane. And that was open for about 20 years, whether you can beat 1.5 times optimal, and finally, 20 years later, in the mid-90s, Aurora showed that you can do it arbitrarily close to optimal. Of course, there's a price you pay here. This will be polynomial time, but it'll be polynomial with degree inversely proportional to epsilon. So if you want to do it to 1.1 times optimal, to 1 epsilon being 1/10, the degree of the polynomial of the runtime will be n to the 1/10th, which is n to the 10. So the exponent of the polynomial will be inversely proportional to the accuracy of the approximation. But that's a price you pay. You expect to pay something for higher and higher accuracy to solve an NP-complete problem. Okay, any questions about this? All right, so that's how heuristics go. And next time we'll talk about graph isomorphisms, and we'll talk about zero-knowledge proofs, which are really, really cool.